Okay, so let's continue our discussion on identification spaces. On identification spaces. Okay. So what we did in the previous lecture was we gave a certain definition of identification spaces, and the definition was solely given in terms of partitions, right? If you recall. So let me just give uh, statements regarding how the identification topology works. But before doing that, let me first approach in a way. Okay. So how did we define the topology, the identification spaces in the previous lecture? So what we did is that, so we start with a topological space. We start with a topological space X, and to identify points in X, say A and B, we relate them in terms of an equivalence relation. Suppose this, we consider the collection of all equivalence classes, induced by this relation on X, and denote this relation as denote this space, the new space we get by considering the collection of all equivalence classes, this space as X quotient this relation. Okay, this is a symbolic notation. This just means that we are identifying the points with respect to this relation over X. Okay. Consider the map pi from X to X, the quotient space induced by X, with pi sending each element X to the equivalence class it lies in under this equivalence relation. Okay. Pi has a property, or rather we topologize X quotient by this pi rather we topologize X quotient to be the finest topology such that pi is continuous. That is, we topologize this space. Suppose I write this space as Y, and that will be the symbol we will be using throughout. That is, a subset of Y is open, obviously in Y, if and only if the pre-image of this set under pi is open in X. Clear? Okay. So this was the way in which we try to define or identify spaces, and a sort of a more general notion, but which exactly characterizes this exact definition, is in terms of simply partitions. Okay. So suppose equivalent definition, and these two definitions are exactly identical. You will be getting to know why I am trying to say this. But the equivalent definition, whenever I talk about identification spaces arbitrarily, that whenever I talk about, suppose I start with the topological space and I say that Y is the identification space of X, I mean identification space in terms of this definition. Okay. So equivalent definition, but later we will characterize the other definition which I will be giving eventually, and then there will be no confusion about what sort of an identification space I am trying to talk about. So I have an equivalent definition. So this definition is solely in terms of partitions. Okay, so how do I define that? Let X be a topological space. Let X be a topological space, and let P be a partition on X. Okay, so what do I do? Consider a space Y where each subset of P resembles a point, and topologize Y using and topologize Y with respect to the map pi from X to Y, which sends each X in capital X to the subset of P it lies in. So the how do we topologize? By the, so it is exactly the same, by the finest topology such that pi is continuous, which means that a subset is open in Y if and only if the inverse image of that subset in terms of pi is open in X. Clear? So now see, what are the things which you are trying to do. So I have a space X, and I have 2 points like this, A and B, and what I am trying to do is that I am identifying both of these to a single point, say P, and I am constructing another set X quotient this. Okay, so this specifically means that A and B are related. So if they are related, they will fall under the same partition, right? And any other related elements to A and B specifically, they will all fall under the same partitions, and eventually this whole partition will resemble a single point in P, and the process is in that form. The thing is that we can actually relate partitions and equivalent sets, and that is a very basic justification, that if I start with an equivalence relation, I can define partitions in terms of equivalence classes. But if I start with partitions, just what you can do is that just define a relation between two elements which lie in the same partition, and that will eventually give you an equivalence relation. The equivalence classes of this relation will resemble the exact partitions you started with. So these two definitions are basically equivalent in terms of the statements we use to define. But now what I want to do is that I want to come to this exact definition from a different point of view. Okay, so what I do is that, so definition, let f from X to Y be a surjective map, okay. Define the quotient topology on Y to be in this way. So how do we define the quotient topology on Y? U in Y is open if and only if F inverse of U is open in X, right? I guess you already are having some hint of how we are setting this topology. And in fact, with this definition, I can actually justify the statement which I have been continuously using, that we are trying to define the finest topology such that this thing happens. Okay, so I can actually present this as a lemma. That the quotient topology on Y is the largest topology such that f is continuous. And how do I actually do that? So this proof is pretty simple. Suppose we have a larger topology on X. Suppose tau is a larger topology on X, on Y. but this implies there exists some u which is subset of y such that u is in tau, but u is not open in the quotient topology, right. But this will specifically imply that f inverse s is not open in X, right. But this will eventually imply that implies f is not continuous, because we know that the definition of continuity follows from the fact that if I start with an open set in the codomain, the inverse image must be open in the domain set, right. Therefore, this quotient topology has to be the largest topology, finest topology, right. And in fact, checking this to be a topology is quite easy to do. Now let us get back to what we were starting with. So how can I actually characterize both of these definitions to be exact or equivalent? See, suppose this is my space X and this is my space Y. I define a map X to Y via F, and specifically this map is onto, and I want this map to be continuous. That is my exact thing to do, but we can actually suffice with it being just onto at this point. Okay. Now, since it is onto, so every element will have a pre-image in X. Okay. So suppose I start with an element Y here. So it will have a certain pre-image here, but clearly this pre-image need not be a singleton set, because we are not concerned about whether f is injective or not. So this pre-image will be some subset of X. Clear? This pre-image will be some subset of X. Got it? And in a similar way, we can define multiple such subsets. So they can map this back as f inverse of z to suppose this part, and I can continue this formation, right. Clear? And these fibers, clearly these fibers partitions X. So what do I mean by fibers? By fibers I mean inverse image of these sets. So a fiber of f with respect to y means f inverse y, the subset which represents f inverse y. So these fibers partitions X. Why is it so? Because first of all, if I continue taking these fibers, I will eventually get exhausted, because f is an onto function, and so I will get sets in this way, and if I do the union of all these sets, I will eventually get the whole of X. The point relies on the fact that these fibers actually are disjoint, and that the reason is very simple. That is, if I have 2 points in the same partition, then both of these points will get mapped to y, right. Are you getting my point? See, this f inverse y, what does this basically represent? This represents f inverse of y, right. Clear? So if I have so what I am trying to say is that if I have an overlap, suppose I have an overlap in this way, then the points in this overlap, suppose I have a point small x here, then x will get mapped to y, being an element of the fiber of y, and eventually it will get mapped to z as well, being also an element from z. So this cannot be possible because we have a well defined function f, right. So that is the reason why these fibers will not intersect at all, and in fact this will partition X. Therefore partitions and surjective maps are equivalent, and since partitions and surjective maps are equivalent, and both of these definitions hence become equivalent, right, because this map is called the identification map. Okay, this map we defined when we defined the quotient topology in terms of a function. So this is called the identification map, or also you can call this the quotient map. This is the identification map, and this pi is also called the identification map, but at this point both of them are making different sense in the way that pi is being characterized by starting the definition in terms of partitions, while in case of f we are starting the definition in terms of a surjective map, but we now see that surjective maps and partitions are basically equivalent. Therefore, both of these definitions are equivalent. Okay. But to this I can add a small remark, and then this thing will be more clear. Let's define this. So how should I define this up? Let me just think a bit. Suppose I do it in this way. Wait, I need to frame up. I had framed up a definition to give it in this way. Okay, let me do it in this way. So let X be a topological space. Let X be a topological space and Y be its identification space. Y be its identification space. So whenever I said identification space, I mean identification space in terms of partitions. So and Y be its identification space with respect to the identification map, with respect to the identification map pi. Okay. So I am just summarizing whatever I did. Now let f from x to y be on 2, and suppose let it be in this way. Okay, so let f from x to y be on 2, and suppose this. Okay, let I'm getting a bit confused to give this actually. So suppose I do it in this way. Okay. See, what I'm actually trying to say is that if I define these both of these identification maps, then actually I will eventually get a homeomorphism. That's exactly what I'm trying to say, but I'm not getting a fine enough statement to do this. Okay, let me do this in this way. Okay. Let f from x to y be on 2, and suppose the topology on y is largest such that f is continuous. Okay. Now any function f from x to y gives rise to a partition, which we just saw, gives rise to a partition of x with respect to the fibers. So f inverse of the singleton set y, for example. Okay, for each small y in capital Y. Okay, let y star denote the identification space, of x in terms of this partition. Okay, now I am good to go. In terms of this partition, okay, in terms of this partition, and pi from x to y star be the natural identification map, then y is homeomorphic to y star. That's what I'm exactly trying to say. Okay, so what are we typically doing is that we first take this definition into consideration, which we defined previously in terms of functions, the quotient map, and then what we are doing, we are considering the partitions with respect to this onto map, and with respect to these partitions we are defining another identification space of x, y star, and then we are saying that y is homeomorphic to y star. Okay, I guess now it all makes sense. So how should I prove it? The proof is fairly simple. We know since y star is an identification space, so the points in y star are these fibers over y, right, such that y is in capital Y. what I do is basically I define a map from y star to y, and how do I define this? I define it as, so it sends this to, so where should I send it out? Yeah, I'm sending it to y. That makes complete sense. Okay. How is it useful? Observe that h pi is f, right, and this implies h inverse f is pi, right? Clear? So h pi is f because pi is the identification map. So if pi is the identification map, then it's naturally continuous. So see, we know this, that, so this is a very easy demonstration, that if you have a function f from x to y and you have a function g from y to z, such that g and f both are continuous on x and y respectively, then gf, that is g of f from x to z, is continuous, and I have a 1-1 correspondence in this case as well. I have an if and, sorry, not 1-1 correspondence, I have an if and only statement in this case. I can go around from both sides. In fact, I can go around from both sides. I should not say this in terms of arbitrary functions. To prove this, you need to make sense of something more. See, what I'm trying to say is that if, so let me just add it here. Let y be the identification space. Let y be the identification space of x, and pi from x to y be the identification map. Let z be any topological space. Then what I'm trying to say is that f from y to z is continuous if and only if f pi from x to z is continuous. So if I have this statement in hand, then this proof is done specifically, because then these two statements imply that h and h dash are continuous, h and h inverse are continuous, which gives the respected homeomorphism. Okay. So since we have established this fact, throughout now we will be using the concepts of identification space just in terms of identifying partitions or collapsing partitions. Okay. So let me just add it as a remark. So identification is equivalent to saying collapsing subsets of partitions. Okay. Clear? Okay, how should I prove this statement? I'm not given a proof of this. How should I prove this statement? The proof is fairly simple. If you start with a set u in Z which is open, but this is open if and only if, or I should say that this is open, then f inverse u is open if and only if pi inverse f inverse u is open in X, right? Pi inverse f inverse u is open in X, because pi is the identification map, and this is if and only if f pi whole inverse of u is open in X, and we are good to go. The proof is fairly simple. Clear? Okay. Now we need to characterize some things, because we have done a lot using these identification maps. So we need to present some characterizations of these identification map, that the map, how are we actually collapsing out, or what is the relation between the identified space and the original topological space we started with, because this function is the only attachment which is still there between the identification space and the topological space we started with. Okay. So theorem, let f from x to y be onto if f maps open sets to open sets, open sets to open sets and closed sets to closed sets, either of them will do. Closed sets to closed sets, then F is an identification map. So again, let me just give this out clear. What do I mean by an identification map? So this is the last time I am repeating this. So by an identification map, I mean an onto map from X to Y such that the topology on Y is defined to be the finest topology such that F is continuous. Okay. And in terms of partitions, I will simply define it to be F is a map from X to Y where where Y is the identification space, and F sends each element in X to the subset of the partition which identified this identification space in which X belongs. Okay. So let's give a proof of this. Now see, this proof is fairly simple because let U in Y be open. Okay, let U in Y be open. So I want to get the fact that F is an identification map, right? So let me not start with U in Y be open. Let me in fact start with let U in Y be such that F inverse U is open. F inverse U is open. And we okay, one thing I should make it clear that whenever we are talking about functions, we are talking about continuous functions. I am not specifying that, but we are talking about continuous functions. So let U in B in Y be such that F inverse U is open, then F of F inverse U, which is precisely U since F is onto, is open, because F maps open sets to open sets. And conversely, since F is continuous, if I start U being open in Y, F inverse U is open, right? So converse holds by continuity of Y, and thus F is an identification space. Thus F is an identification space. Okay. Okay. So fine. The next theorem is actually quite important, and this we will be using throughout. So let me just give this name, the theorem star. Okay. So let F be onto from X to Y. In fact, this is in fact a corollary of the theorem we just did. So let F be onto from X to Y, then I am saying that if X is compact and Y is Hausdorff, then F is the identification map. Then F is the identification map. Okay. So proof, and the proof is that, see, simply if I show that F is a closed map, that F sends closed sets to closed sets, I am good to go. Okay. So what I do is that let C be in X be closed. Okay. Since X is compact, C is compact, right? Since X is compact, C is compact, which implies F of C is compact, right? Because continuous image of a compact set is compact. So F of C is compact in Y. Since Y is Hausdorff, we know that compact sets in Hausdorff spaces are closed. Since Y is Hausdorff, F of C is closed, right? Therefore F maps closed sets to closed sets, which imply F is the identification map. F is the identification map. Clear? Okay. So now what we are going to do is that we want a fine mathematical construction of the torus. Okay, and this will be the last part of this lecture. So constructing the torus. I often fumble around in my lecture because all these lectures are not very well prepared. It all comes whenever I am talking through while giving these lectures. Everything comes in my mind while giving this lecture. I don't sit with a well defined notes to start with. I do have some preparation, but that's not actually enough to not talk without fumbling. These are some raw discussions which I present out here. Whatever. So constructing the torus. So to construct the torus, let us first do what's necessary to do, that is the visualization. Okay. So how do we naturally construct the torus? What I do is I start with a square. So I start with a square. So I start let me okay. Yeah. So okay. So yeah, I have it. Okay. So I start with a square, and I have what I do is basically I identify the vertical sides along the same orientation, and I identify the horizontal sides also along the same orientation. Okay. So this is the identification which I want to talk about. I think I have done this in the previous lecture. I don't exactly remember, but let's do it once more. So we first identify the vertical sides. So identifying the vertical sides. So I know to identify the vertical sides, what we need to do, that we just need to fold it around. Okay. So we just need to fold it around, and so this I still have like this, and here also I have something, so I still have it like this. I'm just folding it around to attach them. So these two edges need to be glued or identified together, and eventually I will get a cylinder, right? Eventually I will be getting a cylinder, and so by rolling, what I'm actually having is that I am having the vertical edge still out there. So and there is a fine line which represents the gluing of these two vertical edges. Clear? Clear? Okay. Now from here I want to identify the horizontal edges. Identify the other two edges. And to do that, what I do is that I horizontally place it out. So I place it out like this. Okay. So suppose I have it like this, both are in the same direction, and then I roll it out. So I roll it out in this way to get some sort of a structure like this. Okay. So yeah, I have it like this. Extremely bad drawing. I'm so sorry for it. Yeah. So I have it like this. Okay. So yeah, so I have these arrows here. Okay. So let these be just like given like this. Okay. Both are in the same direction. And then we identify them out. Okay. And then we identify them out to, if I join these two parts, so I want to glue these parts together. So then I get a full circle here and a hole in between, right, which comes out from this hole. So this hole comes to form this hole, and this is the edge I had, which is the gluing of this part, and there is one more edge I have, which is basically the gluing of the vertical edges. Now what I claim is that a torus is homeomorphic to S1 cross S1. What is S1? S1 is typically the unit circle. S1 is the unit circle. Okay, this is my claim. Okay. So before moving on to this claim, And see, an intuitive viewpoint to have this claim is that, see, this torus is actually identified by this circle, which is one S1, and this another circle which resembles another S1. So I have two copies of S1, I cross them out as a product space, you can think of it like that, to get this torus homeomorphism at least. Clear? Okay. So before moving on to this claim, let me first give that how we are actually identifying the cylinder to the torus, the square to the torus. Okay. So let x be, so how are we having this square? We are having a unit square. So I can give the unit square as the closed interval 0 1 cross the closed interval 0 1, right? Let x be considered as a subset of E2, sorry, R2, let me use this R2, and since we are talking about subset, with the subspace topology, with the subspace topology, I should have used the word subspace there, let it be, with the subspace topology. Now we partition X as follows, and this is another way of saying that how are we identifying the points. So let me just go back to there once. So we are identifying the points here. So a point here will be of the form 1 y, and a point here will be of the form 0 y. A point here will be of the form x1, and a point here will be of the form x0. So we are identifying these 2 points, and we are identifying these 2 points for all y's and for all x, and all the other points are left apart. And specifically we just identify all these vertex together, okay, which eventually gets actually these 4 vertex actually gets identified together. These 4 vertex gets collapsed to a single point, because this will get identified here, this will get identified here, this will get identified with this, and this will get identified with this, right? So now let me give the precise definition of how this partition takes place. So what are we actually doing? We are identifying the points x0 with the points x1 for all x. We are identifying the points 0 y to the points 1 y for all y, and these two generate the relation we require, right? These 2 points generate the equation we require. So suppose I simply write this as this relation, then x, where x was equals to 0 1 closed interval 0 1 cross closed interval 0 1, this gives me the torus. But explicitly writing the partitions will help out more. So what does the partitions induced by this relation? Partitions. So clearly one partition specifically we will be getting of this form. So elements of the form x0 and x1, because each x0 is identified to each x1, and this happens for all such that 0 is less than x is less than 1. Because we are separately identifying the vertices, so I am not including zeros and ones here, because if I include zeros and ones, I will eventually get to the vertex point. So I am excluding the vertex, the 4 vertices. Then I will have 0 y to identify with 1 y, such that 0 less than y less than 1, right? See, these represent the each equivalence classes of elements of this form, right? These actually represent the equivalence classes of the element x comma 0 under tilde, right? Just work it out, it's quite easy to observe, because for each x, x0 will be related to x1 only, because we are identifying the points x0 and x1. So in the equivalence class I will have both, so since x1 and x0 are related to each other, so in the equivalence class of x0 I will have x1 as well, and that is the only point there should be there. Number 3, now we identify the 4 vertices, therefore I have a specific partition which consists of the point 0 0 0 1 1 1 and 1 0, the 4 vertices. And fourthly, I have all other points except these specific points which have been considered in these cases. So all the points of the form x y, such that 0 is less than x less than 1, 0 is less than y is less than 1. And you can easily observe that these are just singleton sets, right? Clear? Okay. So with respect to these identification spaces, we will eventually get to the torus. Okay. And how we are getting the torus, that's geometrically given. Now what we want to do is that we want to show the homeomorphism between so I want to show the homeomorphism between the torus and S1 cross S1. That's exactly what I want to do, right? So let's do that out, and afterwards I will define one more thing to I need to clarify that out. I will do that after having this homeomorphism. So consider the map. Okay, I guess I need to discuss something some things more before this, and then it will be clearer to have this homeomorphism into mind. Okay, so see, let me think of how to do this. Okay, see, suppose I start with some space x. See, pi is suppose a map from x to y. Okay, and suppose this is the, I want to check whether this is the identification map or not. Okay, okay, let me do this. Let me first prove it out, and then I will be giving out an example of the construction of a Mobius strip, and then we will be continuing. Okay, so yeah, so we want to show, that the torus, which I write as T2, is homeomorphic to S1 cross S1, and to do this we just need a function. Okay, so what I do, I define a function f from 0 comma 1 cross 0 comma 1 to S1 cross S1 such that f of xy is mapped to e to the power 2 pi I x e to the power 2 pi I y. And why do I specifically do that? Because if I consider a unit circle, I can consider the unit circle if I do. So I can consider this to be in a complex plane, because I can consider this to be in R2, and R2 is topologically equivalent to complex plane. So each point on S1 I can identify as e to the power 2 pi Ix by the polar form or by the Euler form. So I send x to e to the power 2 pi Ix and y to e to the power 2 pi Iy. But then you can easily observe that therefore f is a homeomorphism. F is easily a homeomorphism, and this is the exact homeomorphism you require. Clear? Got it? Okay. Yeah, I think we're good to go, but I want to end this lecture with one important sort of, have I done this in the previous lecture? Let me first check once. I often forgot what I do in the previous lecture. I think I started with a Mobius strip itself, right? Or no, I started with a torus. Yeah, I gave the concept of a Mobius strip. Okay, I haven't even given what I wanted to say. Okay, so let's get back to the page we were on. Okay, so yeah, so what I want to specifically discuss is that the way I am trying to say the concepts of open sets, how they are actually carrying out in terms of visualization. Okay, so let me start with an example. So let us recall how we constructed the Mobius strip. Okay, so recall construction of Mobius strip. Okay. So how we constructed the Mobius strip? We started with a rectangle R. We identified this edge and this edge with reverse orientation, and from here we got the Mobius strip, right? So yeah, so I got the Mobius strip. I'm not showing the construction once more, because you can just go back to the previous lecture and have this. I am writing this identification space to be M. So this is in fact an identification space, right? I'm having this identification space to be M, and the partitions which give this space, let me just write that only once. The partitions which give this space are, number 1, the sets containing. So we are identifying each point here. So a point, so suppose this is 0 comma, so this is the line 0 and this is the line 3. So a point here is 0 y, and I'm mapping this to 3 1 minus y, right? So I am having here 1, right? Okay, so I'm mapping these 2 points out in this way. So sets containing points of the form 0 y and 3 1 minus y for all 0 less than equals to y less than equals to 1, and singleton sets of all other points. So this is basically how we had the characterization, and what we are doing is basically, so I can think of just having an equivalence relation. So this basically means that I am relating 0 y to the point 3 times 3 and 1 comma y, right? So now what I am doing, I am having the identification map, which we already know. So I am having the identification map pi from R to M, where M is obviously the notation for the Mobius strip which we have got by identifying R in certain conditions. So I know that I need to set some element R, I need to send it to the subset of the partition which contains R. In fact, that is exactly the equivalence class of R, right? And the way we define the topology on M is that this map pi is the topology should be larger such that this pi is continuous, right? Clear? Okay. Now let R star be R minus the vertical edges. So I am just considering this space, excluding these vertical edges. You can easily observe that every point except the ones on these vertical edges, they, suppose a point, I am choosing a point R, suppose here, this point R will get mapped to the singleton set R in M, right? And clearly then this map is injective, right? Clearly then this map is injective. So then the map pi restricted to R star is injective, right? This is the first case to observe, and in fact it is a homeomorphism. In fact, a homeomorphism, because I have already defined the topology on M to be such that any subset of M to be so this is in fact a homeomorphism from R star to M minus L, where L is the image of the vertical edges of R under pi, right? Now how does this homeomorphism follow? Because we have defined the topology on M in such a way that a set O is a subset O in M is open if and only if F inverse O is open in R star. So in fact this will give a homeomorphism from R star to M minus L, because we are excluding the vertical sides of R, and we are left with a 1 1 onto map. That's exactly what we are concerned about in this case. We are left with a 1 1 onto map, because if I start with a point in M minus L, that point will be of the form some singleton set X, but then I can identify this singleton set X with respect to the point X in R, or specifically R star. So this map is a 1 1 onto map, and in fact it is continuous from both sides, so it's a homeomorphism typically, right? Right? I guess this part is clear. Now the thing is that how are the neighborhoods carried? That's exactly what I want to discuss, that how are the neighborhoods of points are carried from the space to the identification space. So I want to check. Now see, we have already have the fact that R star, which is R minus the edges identified, is homeomorphic to M minus L, right? Therefore, the way the neighborhood is carried from R star to M minus L is trivial, right? The neighborhoods get carried identically to the neighborhoods, right? There is nothing complicated in this case. The complication arises whenever we want to identify the neighborhoods under this map pi for a point on the vertical edges. Okay, so let me do it in this way. So let P be a point on L. Okay, let P be a point on L. Then pi inverse P. So what should be the images pi inverse P? So these should be the points of the form 0 y and the point 3 1 minus y for some, because both of these points are getting mapped to P, right, under the identification map, for some 0 less than equals to y less than equals to 1. So in terms of neighborhood, what we are actually getting is that, so I start with this rectangle. I suppose I have this point 0 y and I have this point 3 1 minus y, and suppose this is the Mobius strip. So let me draw it in this way. Yeah, okay, suppose I have this Mobius strip, and suppose this is the line L. Okay, suppose this is the line L, this is the point P. So this neighborhood is basically of this form, right? This neighborhood is specifically carried by considering this to be identified as a subspace of R3, for example. Okay, but then this neighborhood is actually characterized by 2 points. So therefore I will have a half disk here, a half open disk here, and the half open disk here, right? Then if both of these points are carried out to P, these neighborhoods will get carried and they will just identified again as the points are getting identified and form the open set around P, open neighborhood around P. But the thing to keep in mind is that pi is not an open mapping. Pi is not an open mapping. And why is it so? Why is it so? Because if you observe that I am considering this rectangle inside R2, right? Every open set is in term of some open disk. So actually I am having this as an open disk. But since I am considering a subspace topology here, suppose this open disk is say B2. So suppose I am having since I am having a subspace topology on R, so this open set, suppose this open set is given as let's say U. So I am having U intersection R to be the open set B2, right? That's from where that's why I am getting this half open disk to be open in R, but a half open disk won't be open in this Mobius strip, right? Okay, so that's all for this lecture. In the next lecture we will be straight away moving on to the construction of a cone, and we will be showing the topological equivalence of the geometric cone and the algebraic cone or the simple cone on X. And after that we will discuss some properties of this identification map. Later on we will discuss the identification map of B2 over S1, which will be a quite interesting topic to talk about. And I won't be discussing projective spaces as such, but I might talk about some operations later. So meet you guys in the next lecture.